what we'd like to do in this chapter is to solve the Schrodinger equation in one dimension and look for what we call stationary states, or in other words, energy eigenvalues and eigenfunctions. So, here we've got the Schrodinger equation, again in just one dimension. We'll get to 3 dimensions later, do the hydrogen atom and fun things like that, but you got to walk before you run. So, we're going to only examine potentials that are not functions of time. So they're constant in time, but not in space. This will allow us to employ the separation of variables technique in the solution of this partial differential equation. So what I'm going to do is I'm going to assume I can write psi of x and t as a product of solutions, little psi of x times some function of t. These solutions will be of use to us, even though it seems like only a few problems can be solved exactly like this. Well, let's do this. I can write d psi dt as psi times df dt, if I look at this equation above it, and I can write the second derivative of psi with respect to x as f times d squared psi dx squared. That being the case, I can rewrite the Schrodinger equation as I h bar psi df dt is equal to minus h bar squared over 2m, second derivative of psi with respect to x, f plus v times psi times f. What I want to do is divide through by psi times f. And when I do, what I get is I h bar over f df dt is equal to minus h bar squared over 2m, 1 over psi, second derivative of psi with respect to x, plus b. The only way this equation can hold is if both sides are equal to a constant. There's no way to get these two sides to be equivalent unless each of the sides is equal to the same constant. Let's call the constant E. That's pretty suggestive because, of course, we mean energy. So if I look at the first, on the left-hand side of the equation, I'll get df dt is equal to minus IEF over h bar. And on the right-hand side of the equation, I get minus h bar squared over 2m psi, second derivative of psi with respect to x, plus b is also equal to e. Now, I can look at this left-hand equation first. I can solve the t equation really easily. T. Separate variables, and I'm going to get df over f is equal to minus I e t dt over h bar. Integrate both sides, and of course I get f of t is equal to some constant times e to the minus I e t over h bar. This one I can, sorry, 2m. For this equation, I can insert all kinds of potentials and find the energies and wave functions that result. So what are the advantages of using this approach? Advantages. A separable solution. all solutions are stationary states. If I find the energy for one time, it's the energy for all times. What that means then is even though psi of x and t depends on time, psi of x and t squared does not depend on time. In addition, if I calculate the expectation value of any variable, the time dependence also cancels. So suppose q is some variable. If I have q as a function of x and p, and I want to find its expectation value, I write it as psi star times q of x h bar over I d dx psi dx. I have no time dependence there either. Also, in this case, x is constant, expectation value of x is constant, expectation value of p is 0. Second advantage, the solutions are states that have definite total energy E. So my new sort of total energy equations, my Hamiltonian operator, I'll write as minus h bar squared over 2m second derivative with respect to x plus d of x. And of course, I'm applying it to psi. And I can very simply rewrite the time-independent Schrodinger equation in the following way. I can just write it as h psi is equal to E psi, where here are my energy eigenvalues. Third advantage, the general solution is a linear combination of separable solutions. This means that for every allowed energy, there's a corresponding wave function. So you can say psi 1 of x and t is equal to psi 1, whatever I get from the time-independent solution, times e to the minus e1 t over h bar. And let's say psi 2 of x and t similarly is psi 2 e to the minus I e2 t over h bar. I can write the general solution as psi of x and t is equal to the sum of m equals 1 to infinity, c sub m psi sub m of x e to the minus I e m t over h bar. Now we can write every solution of the time-independent equation in this form. All we have to do is calculate all the c's. So this is a really nice method to use, and we'll use it for probably, well, one of the simplest and classic quantum mechanics problems, the particle in the box. So let's do our first real example of solving the Schrodinger equation for a particle that's essentially in an infinite dimension. So here's a box, a one-dimensional box is a length A. Particle is located in here somewhere. Turns out the potential B of x, and this is x equals 0, x equals A. B of x is equal to 0 for 0 less than or equal to x less than or equal to A, and is equal to infinite everywhere else. In other words, the particle's inside the box, it's never getting out because the potential's so high it can't escape. Wave function should have some finite value inside the box, but outside the box the wave function should be 0 because there's essentially zero probability that you're going to find that particle outside the box or outside the well. So inside the box or inside the well, b is equal to 0, and my Schrodinger equation becomes h bar over 2m second derivative of psi with respect to x is equal to e psi. Let's define k, simplify our variables, as 2me over h bar. Therefore, simplifying my dE, it looks like second derivative of psi with respect to x is equal to minus k squared psi. Very simple to solve. We recognize this as a, what function do we know that when we take two derivatives, we get the negative of that function? Of course, that's sines and cosines. So we can write our general solution. Psi of x is equal to a cosine, I'll write it a sine kx plus b cosine kx, where a and b are arbitrary constants, which are fixed by applying boundary conditions to the problem. Usually, we assume psi and d psi dx are continuous at the boundary, but in this case, only psi is continuous at the boundary, not d psi dx. Well, for psi to be continuous at the boundary, it must be that psi of 0 must be equal to psi of a, and of course must be equal to 0 since it's 0 outside. So I write psi of 0 is equal to a sine k times 0 plus b cosine k times 0. Notice if this is 0, it has to be a sine k, it will always be 0. B has to be 0. We must call b 0 in order to make this equation 0. So at the other boundary, we can say psi of a is equal to a sine ka. And that must also equal 0, which means a can't be 0, so sine ka must be 0. So that means ka must be equal to some integral multiple of pi, because the sine of pi, 2 pi, 3 pi, 4 are all 0. So we're going to write k as n pi. So my choices for ka are 0 or n pi. Therefore, I'm going to write k sub n as square root of 2m e sub n over h bar. And so my energies, if I plug that back into the system, my energies as represented by n are h bar squared k squared over 2m, but k has values n pi over a, so I can write that as n squared pi squared h bar squared over 2m a squared. Those are my energy eigenvalues for the particle in the box. Notice that the energies are quantized. If it were a classical particle, it have any old energies. But in this case, these energies are quantized because we have the variable n in there. If I want to find a, I have to normalize the function. So I'm going to say that if I take that function, sine squared kx dx, integrate from 0 to a, because the particle has to be somewhere in the box, that integral has to equal 1. That tells me that if I do this integral, I'm going to get that a is equal to the square root of 2 over little a, and therefore my eigenfunction psi of x sub n is equal to the square root of 2 over a sine of n pi x over a. So those are my eigenvalues, my energy eigenvalues and energy eigenfunctions for the particle in the box. Notice some interesting things. If I were to plot psi of x as a function of x, 0 to a, notice what happens. Psi 1 of x, where n is 1, gives me a graph that looks like this. Psi 2 of x gives me something that looks like this. Psi 3 of x gives me 3 humps. From 0 to a. And this is very much akin to standing waves on a string. Psi 1 is what we call the ground state, and we call the other psi 2, psi 3, etc., we call them excited states. Properties of these solutions. First of all, the functions are alternatively even or odd with respect to the center of the well. Obviously, that's an even function, that's an odd function, and they alternate that way. Each successive state has one more node. See an extra loop each time around. The sides are mutually orthogonal. So in other words, if I were to integrate psi m star psi n over all space, one's an odd function, one's an even function, that's going to give me 0 for m not equal to n. And if I combine the fact that they're normalized with the fact that they're orthogonal, I get, of course, that they're orthonormal, which tells me if I integrate psi m star x psi n of x, that will give me dx, will give me delta m n. Okay, where m is, where that's equal to 1 if m is equal to n, 0 if m is not equal to n. My psi's are also complete because any other function f of x can be written as can be expanded in that way. I can write f of x as sum n equals 1 to infinity c sub n psi sub n of x, which I can write as the square root of 2 over a, sum n equals 1 to infinity c n psi n pi x over a. Notice, this equation is one way of writing the Fourier series for f of x. And of course, we can expand any function as a Fourier series if we want to. We can also evaluate my c sub n coefficients by the following maneuver. Multiply both sides of the previous equation by psi m star and integrate. So notice what happens. I'm integrating psi m of x star times psi n of x dx. That's equal to sum n equals 1 c sub n integral psi m star of x psi n of x dx. Notice the fact that I have a delta mn, that's going to kill every term except the n equals n term. So I can simply write psi integral of psi m star of x f of x dx as sum n equals 1 to infinity c sub n delta mn, or just c sub n. So what we've talked about, these 4 previous properties are extremely powerful, and they don't just pertain to the square well. We're going to find alternate odd and even functions whenever the potential is an even function. every successive state will always have one more node. That's always true. Orthogonality will also always be true. And completeness will be true in general. It's hard to prove, but we're just going to assume it. So, putting everything together, we can throw in even the time dependence, because that's just a simple multiplication. Feels like you're sledgehammering a peanut, but psi of x and t for this particle in the box, square root of 2 over a, sine n pi x over a, e to the minus I, and the energy is n squared pi squared h bar squared over 2ma squared times t. So the most general solution is a combination of these stationary states. So I'm going to write this as all that times, let me insert sum n equals 1 to infinity, c sub n times that whole mess. Or, if I like, I can write this as cx0 as just the sum c sub n psi sub n x n equals 1 to infinity. And then, of course, just for completeness, c sub n then is written as square root 2 over a, integral 0 to a, sine n pi x over a dx, psi of x and 0. And that's how I get my coefficients. So if I'm given psi of x and 0, or I can find psi of x and 0, I can compute the c sub n's, and I can compute all the dynamical quantities I'd like to. So that's a really simple example. And we're going to go from that to a much, much more challenging example called the harmonic oscillator. We're going to take two different approaches. One is a too cute for its own good approach, but it's an amazingly useful way of proceeding, and it's used in field theory all over. The other is the brute force, terrible differential equation method. And we'll do both of them so you can see how they work. Most likely, particularly in the way quantum mechanics and field theory and so on are taught and done these days, the operator, the ladder operator approach that we're going to do first is by far the most useful approach, but you should see the differential equation as well, because that's it's something that you should at least see once. So we'll do that next time. That will be a very complicated problem. It's strange that we go from something so trivial as the particle in the box to something that has that much teeth to it, but that's where we will go next. We'll do that next.